this event. No worries. So
Okay.
you take rest. No issues.
Yes, sir. So
Right?
Sarabjit Singh, sir, is joined.
Yes. I am already in the meeting.
Okay. So, sir, we start, sir.
I suppose time is close to 2:30, and we can start. It's up to you.
Uh, yes, sir. Only 2 minutes is left. So we start.
Welcome to the FDP program, sir. Dr. Sabjit Singh is currently working as an associate professor at the Department of Mechanical Engineering, Punjab Engineering College, Chandigarh, India. He is graduated from the Regional Engineering College Jalandhar, as well now called as National Institute of Technology Jalandhar, M.Tech from GNDEC, Ludhiana, and PhD from Indian Institute of Technology, Roorkee. His field of interest includes development and processing of advanced materials, metal matrix composites, polymer metric composites, natural composites, conventional and unconventional machining behavior of composites, micro machining, ECDEM and WECDM process, sustainable manufacturing, etc. He has published more than 70 research publications in the reputed international and national journals, international and national conference, etc. He has guided 2 PhD and 5 are in progress. He has guided 9 MTech and more than 30 BTech projects to the undergraduate students. He attended number of international conferences in India and overseas and delivered expert talks as per the theme of the conference. He delivered expert lecture in the number of STCs or FDPs organized by IITs, NITs and or other reputed institutes or research organizations. He is the reviewer of some of the reputed journals in the field of production and manufacturing such as IJAMT, Material Processing Tech, iMech Part B, Composites, Silicon and many more. Today sir will be delivering the talk about electrochemical discharge machining, a part towards the sustainable manufacturing. Warm welcome to you, sir.
Uh, Thanks a lot for this introduction. So, good afternoon, dear participants. So, I suppose I am interacting with a very learned group, consist of doctors, professors, researchers, as well as students. Uh, so, very good afternoon to all of you. I suppose I am audible to all of you. So, anyone, please respond so that.
Yes, sir,
Yes,
audible,
sir,
sir.
audible, sir.
Audible, sir.
Thank you. Thanks. Thanks a lot. So, let me share my presentation. One minute, please. So, anybody, please confirm.
Yes, sir. This is visible, sir.
So, in fact, I am also suffering from cold, not fever, in fact. So voice will be slightly different. Okay. So, good afternoon, dear participants. So, I myself, Dr. Sarabjit Singh from Punjab Engineering College, deemed to University. So, my topic is electrochemical discharge machining. So, it is known as ECDM, commonly known as the ECDM, that is electrochemical discharge machining. And the topic is path towards sustainable manufacturing. So when I'm talking about, when I came to know the theme of this STC, that is related to the uh, like green manufacturing, green materials, or sustainable materials. So the things came to my mind that I need to mend my presentations towards the theme of this STC, that is green manufacturing, I suppose. So when we are talking about any machining process or manufacturing process, normally we talk about its basic quality characteristics that are in terms of its material removal rate or tool wear or its surface roughness, like that. So um intentionally or unintentionally, we forget to explore the behavior of that process. That process may be any process, maybe any cutting process, maybe a EDM, maybe a ECM, or maybe ultrasonic process, maybe a laser process, laser beam machining process, electron beam machining process, any process. We intentionally or unintentionally forget to explore its behavior towards the operator as well as behavior toward the environment. Right. So that is a very important part, I suppose, we skip in many of the manufacturing process. And in our work, that basically my team is here, which is working on this process, that is electrochemical discharge machining, and we join hand with the NIT Patna also. They are also performing some experiment on some type of composite in our labs. Um, in that one, we basically machine difficult to machine material that we are going to discuss in the coming slides. No issues. So, what I mean to say over here, so we need to talk about the effect of these processes with respect to the environment or with respect to the health of the operator who is going to operate these type of processes. So we that is one of our domain. Although we worked on its material removal rate, also overcut, also material surface roughness, also these type of things are we all already studied. But our main focus is on the sustainable manufacturing in terms of its effect on the environment or on the operators. That is our main motive of this development of this process. So as you see that, let's discuss about this process itself. As you see that this electrochemical discharge machining, this process itself consists of two processes, that is EDM, that is electric discharge machining, and ECM, that is electrochemical machining, right? So we can say that in the very first attempt, we can say that this is a hybrid machining process. In that one, we uses the process capability of the EDM as well as the process capability of the ECM process. So when we are talking about these two processes like EDM and ECM, they are mainly used for conductive materials, right? For example, only conductive we are able to machine, whether that's a micro machining or any kind of machining, we are able to machine only only the conductive materials with the help of EDM or ECM process. So what about the non-conductive materials? When we are talking about the composites or ceramics, these processes, that is EDM and ECM, we are unable to use them, right? So we have another set of non-conventional machining techniques like ultrasonic machining, or we can say with the help of laser. Also, we are able to machine uh, these non-conductive materials, but they have again their added advantages as well as disadvantages. So there is a, I suppose there is a need to develop a process which can machine the conductive as well as non-conductive materials, right? So so in fact, this electrochemical discharge machining, it provides a comprehensive solution to any kind of materials. It means It means with the help of this process, we are able to machine conductive as well as non-conductive material, right? That is the I suppose the most important advantage of this process. So I can say that you give me the material, any material, I am able to machine it with the help of this process. So we already discussed that the need of ECDM is to machine electrically non-conductive materials, and with the help of this one, we are able to attain a better accuracy as well as the surface finish. Because why this second point came into existence, that is better accuracy and surface finish. And as we already pointed out that in the ECDM process, we uses the process capability of both the processes like the EDM as well as the ECM. That's why with the help of playing with the parameters, we are able to attain better accuracy as well as surface finish with the help of this process. Then normally when we are talking about this ECDM process, this process is used to machine with the help of this process we are able to machine the like attempted to machine the micro parts like micro holes, micro channels having the diameters. If I'm talking in terms of holes, that diameter is close to the 200 micron or 250 micron. When I'm talking about in terms of channel, it is in fact less than 200 microns. So it is used to generate the micro channels or micro holes on different ceramic or composite material, or in fact any other material. So some of the researchers, as in this process, some of the researchers did some kind of surface modification, because in this process, this spark is generated, and if you are able to control that spark and able to control its placement of the spark on the surface of any materials, and it is going to change some surface modification. It is going to change the properties of the surface. We call that as a surface modification. That is in terms of change in its uh, grain size, grain boundaries, maybe in change in the micro hardness, maybe in change in the grain structure. Right. That type of this type of attempts has been already made by the researchers. With the help of this ECDM process, they are able to modify the surface of the material. Right. This is one of the most important application of this process. And generating micro grooves and micro hole slots that we already discussed. These are the some of the characteristics, features, or advantages. You can
Excuse me,
say
sir.
advantages of.
Hello. Excuse me, sir.
Yes, please.
Sir, your
Sir,
slide
your
is
slide is
moving.
not moving, sir.
Yeah.
Uh, Light is not moving.
Now it's moving. Yes, sir.
I just see. Oh, it's changing.
It's a change.
Please see. Please, anybody confirm the slides are changing or not?
Yes, sir. Now it's changing, sir. What?
Yes, sir. Now it's in
Okay.
the slide number 3, sir.
Yes, yes. Slide number 3. That is a principle of ECDM. Right?
Yes, sir.
So let's talk about the principle of ECDM, how it works. So one of the very important point when we are talking about this ECDM process, it's a working principle, how it works. So if you see, so it is explained with the help of these four figure A, B, C, and D. So let's discuss all this figure one by one. So as with respect to the
Sir,
EDM process,
hello.
yes.
Sorry, sir. Sir, slide number 3, but you discuss about the slide number 4. In position in sharing mode, it's slide number 3. Hello. The evolution of ECDM.
I am on slide number 4
But
at
sir,
present.
but in this in sharing mode, the evolution of ECDM is comes.
Okay, there may be some lag, I suppose.
Yes, sir. Some like is there. Yes, sir. Then come. Slide number 4 will come, sir.
Okay, wait for a minute. Uh, because no, please check. No, please check. I am on slide number 4. That is the principle of ECDM.
Yes, sir.
Yes,
Yes,
sir.
sir.
Yes, no, it's come. Okay, thank you. Thanks, Vikas. So let's discuss the principle of ECDM. So here, if you see that it consists of 4 figures, that is figure number A, B, C, and D. So with respect to the our well-established processes like this EDM or ECM process, in that one, what we have these type of things are there. That is the tool electrode is there, some type of power supply is there, some type of primary electrode or secondary electrode is there, right? So here, if you see that, so in this particular case, what happened? There is a tool electrode that is okay, that is already available in the EDM as well as in the ECDM. We have a DC supply. Then we have a node. We call that as a auxiliary electrode. And in the EDM or in the ECM process, workpiece also takes part in the circuit. We provide some kind of polarity to the workpiece. Either it is a positive or it is a negative, it depends. Right. If you see this figure number A, so workpiece is not going to part uh, is not going to is not a part of the circuit, right? So how the circuit is completed? The circuit is completed with the help of this electrolyte that is present over here. Right. So this electrolyte mean to say it is like some kind of electrolyte, maybe a NaCl, NaOH, maybe KOH, or any kind of electrolyte is available over here. Right. The circuit is completed from this tool electrode to DC power supply to the anode to the electrolyte, and then again come back to the tool electrode, right? So it means this workpiece is not going to participate in the process. Workpiece is not going to participate in the process. So what happened over here? the- If suppose I'm able to generate a spark during the process, the spark generation is again a different phenomenon that we are going to discuss in the coming slides. If I'm able to generate the spark, then my job is to control that spark and direct that spark on some specified surface of the workpiece. It may be of conductive or it may be of a non-conductive in nature. If I'm able to control that one, it means I'm able to machine that one, right? Spark mean to say that is uh, you can say view flame, or it's like a plasma is there. So its temperature is close to 3500 degrees centigrade, and it is able to melt any of the material over it, right? Right. So very important point of over here is the workpiece is not part of the circuit. That's why we are able to machine any of the material with the help of this process. Okay. So when we apply some kind of DC potential over here, so what happened? This electrolysis, like this electrolyte that is present in the container, some electrolysis processes started. So because of that electrolysis processes, what happened? The hydrogen double generations takes place, and the uh, and this formation is accelerated with the help when we further increases the potential or the voltage of during the process. So what happened? These hydrogen bubbles join together and make a casing or hydrogen film formation on the periphery of the tool electrode like this one. Right? So just see that in the figure number 1, the hydrogen bubbles are formed on the periphery of the tool electrodes, and they, with the increase in the potential, they join these bubbles join together and they make some kind of non-conductive layers on the periphery of the tool electrode, right? With a further increase in the potential, there is a puncturing pressure, puncturing voltage is there. At that, the voltage, this hydrogen gas punctures, and the spark is generated, and we are able to machine the material with the help of this spark, right? So, one of this. This is again explained with the help of one very famous researcher. So that is Wutrich in 2006. He explained all these things with the help of this diagram. Here you see that. So this at point O2A, O2A, there is a start of the electrolysis process, and with the further increase in the potential, here there's a variation in the potential used here. With the further increase in the potential, so what will happen that the hydrogen generation increases, and there B2C, there is a limiting zone where this gas film formation is taking place on the tool electrode, and at the critical point, that is the point C, the puncture of hydrogen film take place and the spark is generated, and with the further increase in the potential, we are able to uh, direct the spark on a specified area and able to machine the material. So this is what about the basic principle of ECDM, that is electrochemical discharge machining. The important point is, but this is not going to part the circuit of the process. So, so this is the one of the very important slides of my presentation. I normally, whenever I talk about the ECDM, I used to discuss these slides a lot because this slide gives you a lot of domains in which the uh, researchers can work, right? So here, if you see that there is, let's discuss all these with one by one. The very first domain is the tool electrode. In this one, we have a number of electrodes are there. We are able to uh, alter their configuration. We are able to alter their hardness. We are able to alter their shape. Shape means to say you can uh, use the profile of that electrode, maybe a square profile, maybe a triangular profile, maybe a circular profile, or any other profile. You provide some kind of textures over there, increase the surface, increase or decrease the surface finish of the tool electrode. There may be change in the material of the electrode. There may be change in the size of the electrode, right? So these type of parameters. With the help of these type of parameters, you related to the tool electrode, you can explore their behavior with respect to the different output quality characteristics. Then the very important thing that is normally discussed by the researchers who are working in this particular domain, that is the ECDM, that is with respect to the electrolyte. Right. So we have basically electrolyte. They are the acidic based electrolyte like HCl, H2SO4. These are the acidic base electrolyte. Then we have alkaline base, that is NaOH, then NaCl, then KOH. These are the some of the alkaline based electrolytes that are basically used by the number of researchers. And there is a concentration of the electrolyte. It may be a 10%, it may be a 20%, 30%, 40%, these type of concentration. The researchers explore in their research articles. So one very important thing that is pointed over here, that is with the increase in the concentration of the electrolyte, there is a chance of increase in the material removal rate and all other parameters. But what we find that during our investigation, we find that with the increase in the concentration, it has a very harmful effect on the operator as well as on the environment. I'm going to discuss all this in the coming slides. So, so during no, we are basically working on how to decrease this concentration. So there is a trade-off between the output quality characteristics, that is in terms of material removal rate or the surface quality of the product with respect to its environmental effect. So we are going to do some kind of trade-off so that we are able to find out the optimal values of this concentration. Or in other words, we are moving towards decrease in the concentration of the electrolyte, or moving towards a green electrolyte, or where the electrolyte concentration is close to 0%. Correct. So apart from this, some researchers also explore the behavior of this abrasive mixed electrolytes. So maybe they mix some kind of aggressive particle, maybe silicon carbide, maybe Al2O3, or maybe any other kind of ceramic reinforcement, that is ceramic material that is mixed with the electrolyte with some concentration, maybe 5% or 10% by the field fraction, and they explore their behavior on the on the on the output quality characteristics. Right. So the second factor, the next factor, that is the temperature. As we know that if there is an increase in the temperature of the electrolyte, kinetics of chemical reaction increases. So with the increase in the kinetic of the chemical reaction, there are the chances that the chemical reaction increases and it further affects the output quality characteristics of the process. So here some of the researchers explore that they increases the temperature up to the 50 degrees centigrade or 55 or 60 degrees centigrade. So they use the different techniques. So one of the techniques that we used in our experimentation, that we go for the localized heating of the electrolyte. Localized mean to say where only where the machining take place, we intend to heat only that portion of the electrolyte where the machining is going to take place, because the effect of that one is it increases the kinetics of the chemical reaction. Further, it uh, uh, we can say that it affects the output quality characteristics of the process. On the other hand, it has a limited effect on the environment, because if you heat the whole electrolyte, that is electrolyte that is close to 2 or 3 liter available in the box. If you heat the whole electrolyte, it has a different effect on the environment. If you heated only the 2 ml or 3 ml electrolyte that is available at the periphery of the machining zone only, then it has a different effect on the environment. So you can play with this electrolyte. This is a number of things you can do with the help with this electrolyte related to this particular process. Then we have a voltage, that is a machining parameters. You can vary the voltage and the effects. Some of the researchers who are working on this voltage, they used to consider this as one of the parameters. But I suppose, uh, as per the literature, uh, close to 40 to 40, 50 degree volt DC volt, you are able to get a good spark. With a further increase in the voltage, that is up to the 60 and 70 the material removal rate. After that, there is no need to further increase the voltage, right? So it is a well-established fact that with the increase in the voltage, the material removal rate increases. So some of the researchers again explore these parameters with reference to the uh, other quality characteristics of the process, right? So after that, we have a pulse duty cycles, that is the on and off cycle of the process. Then we have a pulse duration. Then we have a polarity. Polarity mean to say it is again related to the positive and negative terminal. It is connected to the workpiece or connected to the electrode. Then we have a reverse state polarity or a reverse polarity. Then some of the researchers that explore that is the tool work gap, that is also discussed uh, by the number of researchers and its effect on the output quality characteristics in terms of material removal rate or in terms of that we can say the overcut. Then we have a interelectrode gap. So electrode gap, to see here we are talking about the gap between the uh, cutting tool, cutting electrode, and the auxiliary electrode. As you see, as we see in the previous slides, the cutting electrode or the electrode which is going to cut over here, that is somewhere here, and workpiece is over here, and the secondary electrode is placed at some distance to this one. Here we have a DC power supply. So researchers explore this one also, that is the effect of this auxiliary electrode that is placed at some distance from this uh, cutting electrode, right? Then we have non-conductive or conductive materials as well as the thickness of the workpiece. So here when we are talking about the thickness, so we are able to machine close to the 3 millimeter of the materials, that is close to the 300 microns. So after that, some problems are there. That is, problem mean to say the availability of the electrolyte is restricted or minimized when we increase the thickness of the workpiece material. So we use some kind of hybridization of the process, like some kind of rotation is provided to the machine, some kind of vibration provided to the machine, some kind of you can say we can provide a third generation hybridization of this process, right? Right. So that is so with the help of that one, we are able to attain the uh, we are able to machine the material having higher thickness greater than 2 or 3 mm. So when we are talking about the process parameters, so normally the researchers that they explore the process parameter, that is in terms of voltage that we already discussed, electrolyte concentration, interelectrode gap, pulse on, pulse off, and these are the process parameters. And with respect to this one, we have the output quality characteristics, that is the material removal rate, taper, overcut, then tool wear rate, and some kind of chemical analysis. So here, if you see that when we are talking about the micro machining, when I'm using the word micro machining, then this material removal rate is not considered as a good quality characteristics, because when I'm talking about the micro machining, it means to say the profile or the properties, other properties of the product is more important than the material removal rate. Right. So because if I'm talking about machining of a hole of diameter 200 micron, or interested to make a channel of 200 microns, I'm more interested in that in these dimension rather than rather than this material removal rate. Apart from this, if you see that the removal of material is very small, very small. Like it may be in the range of 0.01 uh, mg, milligram per meter cube, right? So here, if we are talking about this much range of the material removal, then the measurement of this is again a very difficult job. Because we are unable to measure this one. Right? So some of the researchers took this material removal as a parameter, but personally, I'm not interested to take material removal as one of the parameters, one of the output quality characteristics. Then we are talking about the micro machining or the micro business processes. Right? So taper is a very important. So it need to be addressed very carefully during the process. Then overcut is there. Then tool fear rate, that is again important. Then we have a chemical analysis. Now this chemical analysis is basically consists of with respect to its effect on the on the material on the material, as well as its effect on the operator, as well as its effect on the environment. So all these three things we have to uh, consider when we are talking about the chemical analysis. So we explored in our experimentation, we try to explore more on the effect of these parameters on the operator as well as on the environment. So this is again a very important figure. So here, if you see that the researcher worked, it is basically data of last 10 years, and it is already published in our one of our paper. That is the materials that is explored by the worker by the researchers. They are in the range of close to 60% worked on the glass and close to 15% worked on the ceramic. If you see that this superalloy as well as this composite, this is a gray area in which the researchers can perform or study the process behavior. Right. Apart from this, if you see that um, uh, number of researchers they explore only the NaOH that is close to 60%, and again this is a gray area, or you can see that green electrolytes is a gray area where you can work, where you can see what is the effect of these green electrolytes. Right? Apart from this, let's see the tool electrodes. That is, number of researchers use the stainless steel as a tool electrode, then tungsten carbide, brass, tungsten, copper, and other. Other it includes the mathematics or carbon, uh, carbon-based electrodes and something like that. Right? So here again, this material of this tool electrode is again a gray area where you can explore with respect to the stainless steel or with respect to the tungsten carbide. Again, I personally don't like this one. Here, if you see that number of researchers they explore this material removal rate, which I'm not interested here because this ECDM process is a micro machining process, so it's very difficult to measure the material removal rate during the process. So you require a very accurate instrumentations to measure this material removal rate. Okay. Then the researchers explore the hybridization of the process. It means they provide some kind of vibration, some kind of rotation, some kind of abrasive resistance, uh, some kind of laser resistance to this already hybrid process that is in the CPM. Right? Researchers also explore the machining quality, tool electrode, electrolyte, as well as the gas film formation. These are the output quality characteristics that is normally explored by the researchers. So let's talk about the challenges when we are talking about the ECDM process. So if you see that the micro drilling in hydrodynamic design, so here the hydrodynamic design means to say when the depth of our drill hole is greater than the 200 micron, we are in the domain of the hydrodynamic design. So, what will happen in this hydrodynamic design that the availability of the electrolyte, whatever the electrolyte you are using, it is restricted or limited, right? So, the researchers uh, provide some kind of alternative arrangement, alternative solution to this problem by providing some kind of grooves on the with the help of some rotation or providing some kind of grooves on the electrodes or having some kind of force injection of electrolyte in the machining zone. Right? The improvement of drilling surface during ECDM in hydrodynamic design is a challenge to researchers owing to limited supply of fresh electrolyte in machining zone. So this is the one of the ready reference you can say a gap that is available in the literature. So you can work on this one with respect to this ECDM process. The use of ECDM process for machining of non-conductive material is increasing, as we already discussed in the previous slide, where we see that number of researchers are working only on the class that is going to be 60%. When we are talking about um, when we are talking about the other this non-conductive materials, the availability of literature is very limited. So you can explore the more non-conductive materials, maybe in the domain of ceramic, maybe in the domain of zirconia, or maybe in the domain of that silicon crystal. So you can explore more on this one. So apart from this, this is the very important challenge that is we addressed in our research investigation, that is the generation of fume particles during machining and their biological effect on the operator health. So we are able to address this particular gap effectively in during our research investigation. Then collection and characterization of emission product during ECDM and recommendation of green electrolyte which causes least impact on environment and operator health. So evaluation of optimum parametric condition of ECDM process for least generation of fume particles in the breathing zone of the operator during machine. So these are the some of the challenges which we need to address when we are talking about the ECDM process. Right? So up till now, anybody having any queries, any questions, we can discuss. Because after this, I'm going to show you the research findings, what we did in our research investigation. So up till now, anybody having any queries, we can discuss.
I think no queries, sir. Like I think you can proceed, sir.
Okay. So let's discuss the potential area of research in ECDM process. That is the very potential area, that is hybridization of the ECDM process. You can provide a third phase of hybridization of this process by providing some kind of vibration that we already discussed, some kind of laser system, some kind of abrasive particles, some kind of coating on the materials, sorry, coating on the electrode, right? Right? Then effect of deep cryogenic treated two-layer electrode during ECDM process, analysis of machine surface using SEM, machining characteristics during ECDM and laser-assisted hybrid ECDM process. So these are the some of research area that we explored. We explored all these four domains during our investigation on this ECDM process. So some potential search area with respect to environmental aspect of ECDM process. So we have a fume collection and their characterization, fume generation, properties and their effect, biological effect, and environmental aspect of various electrolytes used in ECDM process. Here we explore the acid base as well as the alkaline based electrolyte and study their effect on the environment. So here, if you see how the fumes are collected during the experimentation, so this is the schematic diagram of our experimental setup that we designed in our research lab. So, so it is basically consist of two domains. One is the micro ACTM. Micro ACTM mean to say where some kind of machining is taking place. Right. This one. This is the domain one. You can say this is the domain one. So here, this is the machining is going to take place, and this is the domain two, where we are going to collect the fume uh, generated during the process, right? The fume collection. So here, okay, some kind of machining is going on. Our job is to collect the fume particles. So we designed a setup. The fume collection setup including this consists of a glass filter membrane. It is placed somewhere over here, right? Having this 5 micrometer, 37 millimeter, its diameter is there, and it is basically imported from the China. Then we have a micro pump, and the quality of this micro pump is like that. It is simulated or having properties similar to the inhaling the capability of operators. Right, its pressure is like that. It is similar to the pressure that is you can say inhaled by a human being or a bio operator. Right? So so we call that as a micropump. Right? So the very important point over here is the placement of this cassette. So this placement is ergonomically designed. So some literature is available in the medical related publications, where we found that the placement of the nose, the placement of the nose, or in our experimentation, it is not a nose, it is uh, this fume collection setup that is again simulated with respect to the nose, right? Its placement is at a distance of 200 millimeter from the x direction and 200 millimeter from the y direction, right? So from the ergonomic point of view, we assume that the nose of the operator is placed somewhere here. Yeah, it's placed somewhere here, right? So it is like that. All these fume particles are inhaled by the operator. All these fume particles are inhaled by the operator. And we run this experiment. So we run this experiment for 120 minutes. That is 2 hours in a single stretch, and we perform some kind of analysis on the collected samples that is collected with the help of this fume collection arrangement. So if you see, so this is the actual setup. So we have ECDM process, then we have some uh, this is a micro pump, and this is the placement of the glass filter membrane. So this is the flow chart how we did this thing. We have a ECDM setup, experimental, physical quality characteristics. So material removal rate, least studied. Then we have an environmental aspect. We have overcut, fume particle aerosols. That is, again, we have a gases and compounds that is generated over here. Fume particles or aerosols. We have generated the during the process. Gases and compounds are also generated, and they are found with the help of FTR analysis, and they are formed. They are measured with the help of gravimetric analysis and as well as uh, came to know their existence with the help of FESEM and other techniques. And we have a sample analysis, sample collection, then gravimetrical analysis, morphological analysis, chemical composition, breathing air analysis that is done with the help of this FTR analysis. Right? So this is the process by which we performed our experimentation and their characterization. Then some of the findings that we came to know with the help of this SEM, with the help of EDS or with the help of FTR, we came to know that some analysis, that is the particle size, structure of the fume particle, presence of metallic and carcinogen elements in the fume, and significant presence of toxic gases like CH4 is also available in our FDP. We came to know that this gases is available in the breathing zone of the operator. So these are the some of the findings that we came to know with the help of SEM, EDS, and FDP analysis. So these are the process parameters, so on which we perform our experimentation. That is, the conditions are like this: tool electrode is high carbon steel of this 0.5 millimeter. Auxiliary electrode is a copper. Workpieces, we worked on the carbon fiber reinforced polymer composite of 2 millimeter thick, and applied voltage is in the zone of 40 to 70 volt. Electrolyte concentration is 20 to 50%, duty cycle is 70%, and electrolyte used in our experimentation is again LEOH. If you see that the samples, so here this nomenclature is like it represents the sample that is at a concentration of 20% concentration, and this is 30% concentration, 40, 50. Here the sampling duration is remain constant and the voltage is constant and the duty factor is constant, right? So here we vary the concentration, and in this one we vary the voltage, keeping the concentration of the electrolyte as a constant. So it means we try to perform these experiment using the one factor at a time approach and vary the voltage as well as the concentration. So this process parameter and its effect is recorded over here. Okay, so now let's see a very important point over here. These are the some of the images, same images generated over here. Here, if you see that these are the some of the particles, they are entrapped in our glass filter membrane. So these are the particles entrapped over here, right? So what is these? These are the fume particles. These are the fume particles, right? These are the entrapped somewhere in our glass filter membrane. So what will happen when we measure the dimensions of these particles? These particles are of dimension of, if you see over here, this is a 5.9 micron, and here it is 7.4 micron. So average dimension is comes out to be 8 to 9 microns, right? So it means if you see the level of these particles, it mean to say they are straightway inhaled by the operator. So these particles are straightway inhaled by the operator. So if you see the the diameter of the hairs that is available in our nose, that is close to 70 to 80 microns. So the hairs that is available in our nose, they have the diameter that is 70 to 80 microns. It means to say the the natural filters that is available in our nose in terms of hairs, they are unable to trap these particles because their dimensions are almost close to uh, 1/10 of the diameter of the nose, diameter of the hairs of the nose. Right. So it means they are directly inhaled by the operators and they are deposited somewhere in our lungs or somewhere in our body. This is again related to the particles that is generated during the process. And here, if you found some kind of hexagonal shape of the particles, right? So this hexagonal shape is there, like this one, pentagon shape is there, hexagon shape is there. All these are the fume particles that is inhaled by the operators. Then we came to know the chemical composition. So here, if you see that in the chemical composition, that is chromium is there, uh, silicon carbide is there, then we have titanium is there, chromium is there. So we came to know that during the process, all these particles are having chromium, having titanium, having arsenic. They are inhaled by the operator during the process. Right. That is with the help of EDS analysis. So I skip all these slides. Okay. So I'm going to discuss the effect of all these things later. Let's study the behavior of different electrolyte. So that we discussed the acidic base as well as the alkaline base. So here we discuss the HCl, NaOH, and NaCl. Their behavior with respect to electrolyte concentration, with respect to fume mass concentration is listed over here. If you see that this acidic based uh, electrolytes are going to give you a greater fume mass concentration as compared to this NOH or NaCl, right? So lesser fume mass concentration mean to say lesser fume particle generated, lesser will be inhaled by the operators. So again, if you see that the same images, these are the fume particles that is trapped somewhere in our uh, gas filter membrane. Again, these are the some of the same images that is. Then we have the FTR analysis. So from the FTR analysis, we came to know that the various particle that is inhaled by the operator, that is chromium, nickel, this calcium, iron, copper, sodium, all these are inhaled by the chromium is there. All these are inhaled by the operator. Right? So this is the behavior of the HCl. Okay, now let's summarize all these things. So, what is the effect of all these things? So, we performed the experiment. We came to know that these are happening with respect to the operator, and we explore some medical literature. So, to validate our findings. So, what will be the effect if that is inhaled by the operator, what will be its effect on the health of the operator or health or on the environment. So we try to relate all these things with respect to the medical literature that is available, and we came to know that the size as well as the morphology of these particles, size mean to say the size is close to 8 micron, 10 micron, 15 micron. Morphology mean to say whether they are in triangular shape or in rectangular shape or in hexagon shape. They plays a dominant effect on the human health. For example, if the inhaled particles are circular in nature, they have a different effect. If the inhaled particles having sharp edges, maybe rectangular, maybe a triangular, they have a different effect on the human health. So we came to know that the particles having size less than 10 microns, they are deposited in our lungs and causes serious respiratory problems to the operators. So in our investigation, normally the particle generated are close to 10 micron. So the chemical composition of fume particle reveal presence of numerous elements such as magnesium, the inhalation. Yes, please. Yes, please. Hello. Any question, please? I'm looking for the questions.
Hello, sir.
Yes, please.
Sir, I have a doubt that how you manufacture diameter of 0.5 mm. The tool is so small.
How you?
Sorry, sir.
Please repeat your question.
My question is that you taken the tool of diameter of 0.5 mm, sir. So I want to know, sir, how you manufactured this tool, sir, of 0.5 mm of small diameter.
0.5 mm, that is basically, if you see that these type of tools are already available in the market, that is zero point 0.1 mm, zero point 0.2 mm, zero point 0.3 mm, they are available in the market. We basically used uh, this micro drill bits. That is, you can explore the Amazon or Flipkart, you came to know that all these are available in the market. Not a big deal.
Okay, sir. Sir, one thing, sir, you said that you laser assisted electro discharge machine. So how you developed it, this laser assisted electro discharge machine setup, sir?
Laser assisted. Yes, yes.
Yes, sir.
I'm going to discuss that in the coming slides.
Okay, sir.
So here, if you see that we try to correlate all these findings with the help of our medical literature, and to know that they have the severe effect on the operator as well as on the environment. So all these are already listed over here. So you please read on. There's no fun to read all these things. So if you see that nitrogen dioxide, sulfur dioxide, methane is also available in our gas chromatographic, amides, amino, nitro compounds, aromatic compounds, all these are available. And this causes the serious chronic health diseases to the operators. So, in nutshell, what I want to say that, so whenever we are performing any kind of machining operation, it has effect on the operator as well as it has effect on the environment. So, whenever we are going to design, we have to deal uh, in this domain also. So, I skip all these things and concentrate more on my hybridization process. So here, I suppose you are looking for this thing, that is the hybridization of ECDM. So here, what we did in this experimentation, so we go for localized heating of the electrolyte. We came to that one thing that we concluded from our previous research finding that with the decrease in the electrolyte concentration, we are able to decrease the fume mass concentration. It means if I'm using the electrolyte at a 10%, the less fumes will be generated. It mean to say they have a less effect on the operator as well as on the environment. So if I'm using at a 10% concentration of the electrolyte, my machining, other parameters related to machining, that is in terms of, we can say in terms of material removal rate or other quality characteristic, that decreases, right? So then we explore that, let's try to increase the kinetics of the chemical reaction that occurred during at the periphery of the process. So that is done with the help of hybrid machining process. That is, we use a laser module. We use a laser beam to locally heat the electrolyte. So locally heat mean to say we use a very small laser that is of 500 milliwatt, that is pointed at the periphery of the tool where the actual machining take place, and it increases the kinetics of the reaction. It increases the temperature, which causes that increase in the kinetic of the chemical reaction. And we found that the quality characteristics, there is a significant increase in the quality characteristics of the process, right? With the help of just heating the electrolyte with the help of a localized laser beam. So let's see this one. With the help of laser beam, we are able to attain a stable gas film formation. And these are captured, if you see that, these are the images captured with the help of high-speed shutter camera. Here, if you see that, this is the gas film formation. And here we have a very controlled gas film formation with the help of this laser beam, right? So this gas film formation is again going to control the your quality characteristics, that is the overcut, material removal rate, or any other parameters, right? So although during the process of ECDM, the stray sparking is there. Stray sparking mean to say the sparkings are taking place in this direction also. So therefore, we have to do some kind of trade-off between this one, this straight sparking, so that we are able to attain the desired dimension of the hole, right? For example, if I need to drill a hole of 300 micron 300 micron, then I'm not going to use a tool of 300 micron. I'm going to use a tool of either 150 micron or a 200 micron, so that with the help of stray sparking, I'm able to attain a diameter of 300 micron. So I have to do some kind of trade-off between the process parameter, right? So in this work, an attempt has been made to incorporation of low power laser beam in ECDM process that we already discussed and designated as laser assisted electrochemical discharge machining. The beam of low power laser is focused in the vicinity of the tool electrode during machining, right? So it means ये यहाँ पे machining is going to take place over here. The laser beam is placed at this position. Here I have a laser beam, right? Vicinity of the tool electrode during machining. the main purpose of the laser is to serve as a catalyst. So why this is serve as a catalyst? Because it is going to increase the temperature over here. As you see that here the ambient temperature of the water is close to 20 to 30 degree centigrade. If I perform the experiment at Chandigarh somewhere in the month of June or July, the temperature will be close to 20 to 30 degree in at room condition, right? If with the help of this laser, if I am able to increase the temperature close to 50 to 60 degree centigrade, then there will be a drastic increase in the kinetics of the electrolyte, and it causes a significant change in the output quality characteristics that is done with the help of this laser. The main purpose of the laser is to serve as a catalyst for electrochemical reaction during machining, irrespective of perform machining. The stepped electrochemical reaction and high temperature of the electrolyte responsible for the generation of stable and thinner gas film formation. As you see that here we are able to generate a thinner gas film formation, which is advantageous to us. So just see this figure. This is again captured with the help of a high-speed shutter camera. Here you see that this is basically a drill bit. A spark is generated over here on the drill bit, and having, I suppose its diameter is close to 2.0.2 micron. Sorry, 0.2 millimeter, and this trace sparking is there. If you see that this trace sparking is generated at this face on the drill. So we compared this finding with respect to conventional ECDM process and with respect to laser assisted ECDM, and we came to know that at all these things, at all the parameters, there is a considerable improvement in the quality characteristics of the whole wall. That is in terms of there is a decrease in the overcut, there is a decrease in the overcut with respect to the tool travel rate, decrease in the overcut with respect to the tool rotation, decrease in overcut with respect to the duty cycle. It means in all these domains, the laser assisted provided a significant uh, effect on the output quality characteristics. Here we measured output quality characteristics as a overcut. Then we measured the taper also. And again, we have a significant effect with respect to tool diameter, with respect to tool travel rate, with respect to tool rotation, and with respect to the duty cycle. So if you see that this is the morphological analysis of the laser assisted as well as the ECDM, conventional ECDM. Here with the help of conventional, we have a 780 micron, and here with the help of this one, we have a 732 micron hole diameter. Right. And one more is placed over here, that is 860 micron, and here we have a 818 micron. And apart from this, you can see that the quality of hole generated with the help of laser assisted ECDM is more stable as compared to the conventional ECDM process. So these are some of the benefits that I already discussed in a presentation. So I'm not going to read all this. So this is some step-by-step research contribution that what we did at PEC. We design, develop, and set up, and we find out some quality characteristics and the end results. So at the last, I would like to show you the machining video that is available in our lab. That is a complete video. It consists of a laser, a high-speed shutter camera, and ECDM setup. Sparking is there, machining is there. Please see this. I suppose you are able to see the video.
Yes, sir.
So if you see that the laser beam is pointed at the periphery of the machining process, and machining spark is generated, and laser is pointed over there. Again, I'm going to repeat this. Right, right. So, so this is basically all about my presentation. So I sincerely acknowledge the SERP Science Department of Science and Technology for providing the research grant. Thank you. So I'm going to stop my presentation. So any questions, any queries, we can discuss.
Hello, sir.
Yes, please.
Yes, sir. My question is that, sir, if you're using the ECDM process with micro ECDM, then the metal removal rate is very low. So how can you improve that, sir?
Please repeat the question. If you are using
So if you
ECD
are using micro ECDM, then the
micro,
metal removal, yes, sir, micro tool ECDM, then the metal removal rate is very low. How can you improve the metal removal rates?
uh, in fact, I already said in my presentation, when we are talking about the micro machining, material removal rate is not to be considered as one of the output quality characteristics. The quality of the whole, quality of the end result, whether it is a hole, whether it is a channel, whether it is surface roughness, whatever you are generating over there, the quality is more important than the material removal rate. When particularly we are talking about the micro machining,
Okay.
right? So I advise you, please focus more on the quality.
Okay.
If you are able to increase the material removal rate, but the quality is not up to the mark, right? For example, I'm looking for a hole of 300 micron, but you are giving me a 350 micron. It is of no use,
Okay.
right?
Yes, sir. One thing, if you are
So,
going for a laser assistant ECDM process, I think that there will be tool where will be more in case of laser assisted ECDM process as compared to
tool we are
manual.
exactly, if you see that with the help of the laser, we are able to increase the temperature only in the range of 50 to 60, not more than that,
Okay.
right? So that is basically effect on the electrolyte, not on the material, that is with respect to the workpiece or with respect to the tool,
Okay, sir.
right? Because if like 60 degree is not going to affect have any effect on the tool which is of you can say of a stainless steel or any other kind of material. It is not going to affect. I
Okay,
don't
sir.
think so. It is going to affect.
Okay, sir. Thank you, sir.
So any other questions, please?
Participant, any other question? Hello. Any other question, participant?
I suppose one question is in the chat box.
Okay.
How did you get these research areas? So, Professor Vyas Please repeat your questions. I am unable to get what you want to say in this question. Professor A. Vyas. Sir, please mute yourself and have your question.
Hmm. Hello. Yes.
Yes, yes.
Hello,
Professor
Professor
Vyas.
Vyas. Hello. Are you audible?
So I suppose he is not there.
Yes, sir. He log out the chat box.
Okay.
Yeah, he joined. Professor A. Vyas, can you repeat your question?
Uh, Professor Vyas, are you there?
Voice is not audible, sir. Professor A. Vyas.
I think there
Okay.
is some
Right.
network issue, sir.
Okay.
Okay.
Right.
Professor A. Vyas, if you any query, then you text me. I send to the Dr. Sarabjit Singh, sir, uh, related to any query. So, hello.
Santosh, Santosh, I would like to hear some question from your end also. Santosh, Mr.
San-
Santosh is not here.
Santosh is also not.
Santosh performed the experiment. He's from NIT Patna, and he performed some experiment in our lab.
Yes, sir.
Mm.
Santosh is not there, sir. Santosh.
Right. Right. Okay. No issues.
Okay. So, I think, sir, there is no question from the participant side. Hello.
Yes. Yes. Please.
Yeah, sir. Then there is no question. So we wind up the session, sir.
Right. Right. Thank you. Thank you.
Okay. So, Abhishek, please wind up the session.
Yes, sir. Very good evening, sir. It's very hard to deliver the lecture during this situation, sir. I am very thankful for you, sir. Even during this COVID situation, you have made your time for us and like put lot of effort and delivered the lecture for us. I would like to extend my heartily thanks for you, sir. On behalf of all the coordinator, myself, and participants, I would like to thank you for your time and the lecture. Thank you, sir.
Thanks. Thanks for inviting me. Thanks. Thanks.
Thank you, sir. Thank you so much, sir.
Thank you, sir.
So, dear participants, today's all three sessions are completed. So we meet our third day. So in third day we have in third day we have three technical session. So already I send in schedule. So in schedule all are mentioned. So everyone, so we meet tomorrow at 9:30 p.m. in this platform, and our first technical session start from 9:50. Okay, okay. Again, I thank you to all of you. So we meet tomorrow.
Thank you,
Thank you,
sir.
sir.
Yes, sir.
Thank you, sir. Thank you.
Thank you. Thank you, sir.